In this video we're going to go through the practice problems for test 2. So let's see, what is the SI unit for? Position, it'd be meters. Velocity, meters per second. Time is seconds. Displacement is just change in position, so that's meters. Acceleration is meters per second squared. Mass is in kilograms, not grams, but kilograms. Speed, that's just the magnitude of velocity, so that's also meters per second. Force is in newtons. What newtons means is kilograms meters per second squared, but we call that newtons. Momentum, so momentum is a force times a time, so it's newtons times seconds, or kilogram meters per second. Impulse, same thing, same units. Friction force, well, nothing special about friction. It is a force, so it's measured in newtons. Weight, same thing. Weight is just the force on you due to the Earth's gravity, so that also is newtons. Okay. What is the term for the measure of an object's resistance to a change in motion? That is mass. The more mass you have, the more resistant you are to a change in motion because of a force. Which one of the following refers to the interaction between two objects? That is a force. That is a quantification of the interaction between two objects. What is the term for a force multiplied by the time that it lasts? That's an impulse. The three laws, Newton's three laws. What does Newton's first law state? An object with no forces acting on it will move with constant velocity, or put another way, it'll move in a straight line at constant speed. What does Newton's second law state? Essentially, F equals ma. Net force equals mass times acceleration. The net force acting on an object equals its mass times its acceleration. What is Newton's third law state? Equal and opposite reaction force, right? If a force from A acts on B, then there has to be a force from B that acts on A that is equal in magnitude and opposite in direction. Okay. What does the impulse momentum theorem state? It states that the net impulse on an object equals its change in momentum. And that's why they're in the same units, right? Impulse and momentum are in the same units. That allows this to be true. Number 9, what does the law of conservation of momentum state? In an isolated system, and it is important that you include that caveat because it's not true in general, but in an isolated system, or in a system where there are no external forces, or the external forces add up to 0, the total momentum remains constant. It doesn't change. Okay. For a system consisting of multiple particles, the net external force equals the total mass of the system times the acceleration of the center of mass of the system. So this is F equals ma for systems. And the new part of it is, there's two things. First of all, it's not necessarily all the forces, but it's the net external force, because the internal forces add up to 0 anyway. And the acceleration, there's not one acceleration for the system because it consists of multiple particles that could all have their own accelerations, but it's the acceleration of the center of mass. That's the point, that's the location, this special location of the system that moves according to how the external forces are acting. Okay. All right, now we get to some a numerical one where we'll have to do some calculations. What is the momentum of a 10 kilogram object moving with a velocity of 2.0 I minus 4.5 j meters per second? So this is moving in 2 dimensions. Velocity is given in components. So P is m times v. So it's going to be 10 kilograms times this velocity. And so what we'll get is, we'll get 20 I, because I'm just multiplying by 10 on each component, minus 45 j, and that'll be kilograms meters per second. which is the right units for momentum. Okay, what is it in terms of magnitude and angle now? So this is just some basic vector stuff. We have a vector in component form, 20 to the right and then 45 down. So something like this. That's our p vector. So first of all, the magnitude of p will be the square root of 20 kilogram meters per second squared plus 45 kilogram meters per second squared. I never make my square root symbol long enough at first. And that equals, go to your calculator, 49. The two significant figures, it's 49 kilogram meters per second. So that's the length of this diagonal part of this triangle, 49. What's the angle? Well, we can measure it from the horizontal if we like. That'd probably be the typical thing to do. And then the 45 is the opposite and the 20 is the adjacent. So it'll be the inverse tan of 45 over 20. Those are both kilogram meters per second, so that cancels. I won't bother writing it out of laziness. And we get 66 degrees. So we'll say 66 degrees below the positive horizontal. Oops. Okay, below the positive horizontal. Great. All right. Some more short answer ones. Do each of the following statements make sense in terms of the definition of the terms and their units? The gravitational force from the Earth is 9.80 meters per second squared downward. That does not make sense. That is the acceleration because of that force, but that is not the force. The force would be m times g, right? It would be the mass of the object times this. And we don't even have a mention of a mass. We don't even know what the object we're talking about is. There is no one force from Earth. So this is what the gravitation ends up being if you're in free fall, but that's not the force. Okay. B, the person weighs about 6 newtons. That is correct. That is true. That's the gravitational force on that person. That is this person's mass times 9.80 meters per second squared. Okay. Although I will say 6 newtons is too small. That's an unrealistic number, but in terms of units, it's correct. The static friction between the table and the book has a magnitude of 3.4 newtons. Yes, that makes sense. It should be in newtons because it's friction and that's a force. When the hammer hit the nail, it imparted an impulse of 400 newtons onto the nail. No, that does not make sense. That sentence doesn't make sense. If we're talking about an impulse, we would have to take newtons, which is how strong the force was, and multiply it by seconds, by how long the hammer was pushing down on the nail. Right? That would be an impulse. So this is not the right units for impulse. Okay. True or false? If an object has no forces acting on it, it must be at rest. That is most definitely false, right? That is not what Newton's first law says. Newton's first law says if an object has no forces acting on it, it has constant velocity. It's possible that that velocity is 0, but it does not have to be, right? Think of the astronaut just floating in the middle of outer space. True or false? An object traveling in a circle at constant speed has a constant momentum by the law of conservation of momentum. That is false. If you're traveling in a circle, you have constant speed, perhaps, but you do not have constant velocity, right? Because you're turning. And so the velocity, the direction of your velocity is changing. So there is acceleration, right? There is constant centripetal acceleration pointing inward. And so the momentum would have to change, right? Because P is m times v. So if v is changing in its direction, p is changing in its direction. And furthermore, the law of conservation of momentum does not apply, because if you're going to have constant centripetal acceleration, sorry, not constant, if you're going to have centripetal acceleration, there must be a force, the centripetal force. Something has to be constantly turning the object to keep it traveling in a circle. It could be any one of several kinds of forces, right? Lots of different forces can do it. The tension in a rope could do it, or a normal force, if something's pushing you from behind, could do it. Whatever it is, there is force. And the law of conservation of momentum, you need an isolated system where the force from the outside is zero. So from a couple standpoints, this is a false statement. Okay. Explain the motion of an object that is dropped from a height and allowed to fall through the air, taking air resistance into account. Okay, so what is the story for when an object drops? And we are including air resistance in the story. Well, so it accelerates at 9.80 meters per second squared at first, right at the beginning, but immediately as it picks up speed, the air resistance starts mattering and the acceleration will decrease, because the air resistance is fighting gravity, pushing upward, while gravity is pulling it downward. So it's still dropping and it's still getting faster, but at a lower and lower rate. So the acceleration decreases and eventually to zero. That's when gravity and air resistance are equal, but pushing in opposite directions, and so they kind of cancel each other out. So at that point, so the speed, which at first was growing, starting at zero, will get up to some constant terminal speed or terminal velocity, right? And then it doesn't go past that because the acceleration has gone to zero, so it won't change beyond that. And so it will fall at this constant speed the rest of the way. Okay. A 100-gram object is pushed by a force causing an acceleration of 2 meters per second squared. What is the magnitude of the net force? Okay, so we can use F equals ma here. And we can use it directly. We have the mass, we have the acceleration. 0.100 kilograms. And we do have to convert that to kilograms, the SI unit, times 2 meters per second squared, which I guess gives us 0.200 newtons. That would be the net force. Okay, I will proceed with number 17 in part 2 of this video.